Right. Thank you for the introduction. So let me remind you what happened in previous episodes. So we had a Riemannian manifold. And its tangent bundle, so the tangent bundle had an extra decomposition if you took the tangent bundle to the tangent bundle. So at the point xv, we had the vertical direction, sorry, the horizontal, which was the non-trivial piece of data, and the vertical. And each of them was naturally isomorphic to actually the tangent space at the base point and downstairs. And we had the geodesic vector field, so x, whose component here at xv was just tautologically in the horizontal direction the vector v, and in the vertical direction just 0. And we also have another vector field. So if you can write this formula, you can take the vector field which is 0 in the first coordinate and v in the second. So let me ask you this. What action does this vector field generate? The scaling action, right? So it just moves you up. So this is also known as the Euler vector field. So this generates the scaling action. And if we take the orthogonal complement, so now I'm going to take UM. This is the unit tangent bundle. So this is contained in Tm. So the tangent space to UM, well, it has an x direction, which is the geodesic vector field. And then we have the vertical direction, which is the piece that's orthogonal to v. So v is the point in the tangent space where we're at. And we also have the, sorry, I keep switching horizontal and vertical. So horizontal should always go first, even if I don't always write it this way. So the horizontal and the vertical, so this is inside Txm, and this is also inside Txm. So this has dimensions 1, n minus 1, and n minus 1, where the dimension of m was going to take to be n. So what we showed last time, more or less, I kind of gestured at it, and we showed using the Riccati equation that on this piece, the horizontal plus vertical, the geodesic flow is hyperbolic. So what I mean by that is, roughly speaking, if this is the horizontal direction and this was the vertical direction, then using the Riccati equation, we constructed this kind of open set of so this should be when m has strictly negative, sectional curvature. So we constructed these cones, which depended on how negative or not your curvature was. So if you remember, we had this condition that the curvature tensor had to satisfy so these numbers, k0 squared and k1 squared, with a minus in front, were the bounds on the sectional curvature. So if you divide this, if you move it over here, you just get the usual definition of sectional curvature along a two-plane. And the reason why E, in this case, had to be restricted to be orthogonal to the flow direction is, of course, that if you feed into the curvature tensor two vectors that are pointing in the same direction, you get 0. So you always have to restrict to the orthogonal complement. So for this lecture, I will simply continue assuming this property and just see what kind of things we can deduce about the geodesic flow from this. But I'm going to include on the exercise sheets some further games you can play with the Riccati equation, and you can directly show that vectors, not just the whole hyperplane, but in fact vectors that start in these kinds of cones have to be decaying exponentially in size or growing exponentially in size, depending on how you arrange things. Okay, so these are kind of things you can do with ODEs, but now we want to kind of move on to geometry. Okay, any questions about this? Okay, so in this case, okay, so now we're going to look at the geodesic flow. So the first piece of structure that I want to claim, and I've kind of given some background to it, is that so we have GT invariant decomposition of the tangent at some point xv to um to the unit tangent bundle. So we have what I'm going to call the center direction, the unstable direction, and the stable direction. So, oops. So this is the generated by the flow direction. And these stable and unstable, well, if we have the horizontal and the vertical, they will look something like this. Oops. So if you apply some version of the stable manifold theorem that I mentioned in the first lecture, you will conclude that there exists a foliation. There exist, in fact, two foliations. WU and WS tangent to W, these plane fields. And so the leaves denoted, so, or let me say the leaf through a point P in UM is going to be denoted, let's say WU bracket P, or WS bracket P. And the first main theorem about this geodesic flow is the fact that, so, well, the first observation, which for which you don't need negative curvature is that the geodesic flow preserves a natural volume form on UM. So I said last time, and I didn't keep my promise, I said that I was going to discuss a little bit the symplectic geometry point of view in geodesic flows. And in that case, the preservation of volume is immediate because this geodesic vector field, it's actually a Hamiltonian vector field in some appropriate situation under an appropriate symplectic form. In this picture, again, it's not too bad to prove it either, but I'm just going to take it for granted. So it's a property of all geodesic flows, not just in negative curvature. But in negative curvature, we have an important property is that this volume, volume is ergodic, volume form is ergodic. i.e., for any measurable decomposition we have that the measure of A times the measure of B is equal to 0. So this is just a concise way to say that one of the sets has measure 0 and the other set has full measure. Okay? So I want to prove this theorem, at least sketch a proof, both because we'll need it, but also because I think there's an important argument, which if you haven't seen, it's good to know it. So it's called the Hopf argument. So let me, before I tell you the Hopf argument, I want to
in this section, are we implicitly assuming M is compact or anything?
Yes, I apologize. To have this hyperbolicity, yes, we're assuming that M is compact. You certainly need finiteness of volume. There's a way to, for many of the things that I say, in fact, it's possible to relax it to the case when you don't have finite volume. So you can do the non-compact, where you have finite volume but non-compact. But you need some further assumptions on the curvature tensor. So we spelled it out in the paper precisely what kind of assumptions you need to have a non-compact manifold but of finite volume, plus some assumptions on the curvature, and everything that I say will work in that case. But for simplicity, we can assume M is compact. Did you have another question? Or?
Maybe A and B were divided by the flows.
Oh, yes, yes. Thank you. For any measurable, for any GT, so flow invariant. So I forgot to also give the name to the flow, so I'm going to denote by GT from UM into itself. This is going to be the geodesic flow. And any other questions, any other things I forgot to say, any important assumptions that are implicit but maybe not obvious to somebody who hasn't seen this before? OK, so let me recall the basic theorem in dynamical systems, which is the Birkhoff-ergodic theorem. So it's quite general. So whenever you have, let's say, GT from X to itself, so X mu is a probability measure preserving flow, and F from X to C, so just say F in L1 of X d mu. So whenever we have an integrable function, we have the following property. So let me call this L plus of F of X, defined to be the limit as t goes to plus infinity of 1 over t, the integral from 0 to t of f of gtx dt. So this limit, this exists for almost every x and is GT invariant. So the nice thing about this form of the Birkhoff theorem is that it doesn't tell you, it does not need to assume anything about ergodicity. It just tells you that it produces some function which is measurable. You can see it from the definitions, and which is invariant by the flow. Okay, so this is the kind of basic result in dynamical systems. There's an addendum to it, which I think is oftentimes not emphasized perhaps enough in the statement of this, which is that if we consider the backwards averages, so instead of taking the averages into the future, if we look into the past, so I believe the signs work out correctly for this to be, so if t is negative, then this kind of sign, dt has a negative sign, and this t is negative. So I think the same expression actually can be made to tend to t minus infinity. So of course you can apply the Birkhoff theorem, but the really highly non-trivial fact is that so exists almost everywhere, and L plus of f equals L minus of f, again, almost everywhere. So this equality of forward and backward dynamical averages is, as you'll see in a moment, is not exactly a trivial property. Okay. All right. So now, if we go back to the proof of the theorem. So, in fact, so I claim that it suffices to show for every continuous f, we have that L plus of f, as I defined it over there, is constant almost everywhere. So I added here this convenient assumption of continuous because if your ergodicity failed, you could find a continuous function which had different averages with respect to the two different measures. So the two different pieces that you could decompose. So this is kind of a little cheat that will help a little bit in a moment. So this is importantly equivalently L minus of f. However, L plus of f is, so let me say, so we're taking the forward averages. Yes, L plus of f is constant on leaves of Ws. So what do I mean by that? Let's say we take the this is, remember, this is the contracting foliation, the stable foliation. So if I pick a point here, if I have a point x and I have a point x prime, then asymptotically they approach each other. So for any epsilon, after a certain time, they're perpetually epsilon close to each other. So if I'm taking the averages, these forward averages for x and for x prime, after a certain point, for any epsilon, there will be, after a certain point, within epsilon of each other. Okay? And so if this is true for any epsilon, so these limits, if they exist or not, the answer is the same for all points on the leaf. And if they exist for one point, they exist for the other, and they're equal. Okay? But we also know the kind of dual conclusion for the unstable and for the backwards averages. On leaves of WU and L, either of them. So mostly to simplify the pictures, I'm not drawing the flow direction, but of course there's a flow direction, but we essentially obtain that our function is constant on almost every leaf in such a pattern. Okay? So it would seem that we're done, that this function is constant on these blue curves on almost every, on almost every blue curve, or rather, we have the setup that we have is that we have these measurable curves, affiliation by smooth manifolds. This function is constant on these leaves, on the vertical ones and the horizontal ones, and it would seem like we can say it's just constant, but there's an issue. So there's a warning. So although the leaves are smooth, transversely, so I'll explain this in a moment, the regularity is only Holder. So what it means is the following. So let me just for simplicity concentrate on the unstable foliation. So transversely, you have the following kind of picture that your leaves. So if I take true transversals tau 1 and tau 2, so two little pieces of my work in a chart, I take two manifolds, smooth manifolds which are transverse, I get a map. So this is sometimes called the holonomy map, H tau to tau prime, tau 1 to tau 2. So I have a map from this manifold into this manifold by just following the leaf, the transverse leaf. And in general, this map is only Holder continuous. So even though each leaf is individually smooth, this transverse regularity is only Holder continuous. And if you haven't seen this, there's a very nice article by John Milner called Fubini Foiled, I think. So it's only a 2-page article, and I recommend. I think it's a very nice thing to read. And he constructs in that example, in that article, a family of such a foliation of the square, where the leaves, these horizontal leaves, are in fact real-analytic, and they sweep out the whole square, but have the property that there exists a set of full Lebesgue measure, which intersects each leaf in only one point. So this kind of naive Fubini theorem that you would like to apply fails for these kinds of foliations, for certain foliations, was a discovery, I think, of essentially Anosov, that for the foliations that arise in the case of Anosov systems, he didn't call them Anosov, so he called them U systems, and so people didn't like this name, so then they called them Anosov systems. But so he proved that even though these maps are Holder continuous, he proved that these holonomy maps, H of tau 1, tau 2, are absolutely continuous with respect with respect to Lebesgue measure which means that for a set A inside, let me say tau 1, so Lebesgue measure of A is equal to 0 if and only if Lebesgue measure of H of tau 1, tau 2 of A is equal to 0. So, or to say differently, if you push forward the Lebesgue measure on this leaf, you get a measure that's absolutely continuous with respect to Lebesgue measure on the other leaf. And in fact, you even get a bound on the Jacobian. So the density is bounded from above and from below. Okay? So this is actually a fairly difficult result, so it's not easy to prove. But once you have it, you can go back to this picture and actually argue that this measurable function, which was constant on these leaves and constant on the other leaves, was actually constant Lebesgue almost everywhere. Okay. All right, and then this proves ergodicity of the geodesic flow. Okay. Any questions? All right. So let me just deduce immediately two corollaries. The set of points with dense forward orbit has full measure on UM, and in fact it is saturated by WS leaves. So of course, if a point is forward and if the orbit of one point is dense into the future, then any stably related point, which will asymptotically approach it, will also be dense. And so and of course it is also GT invariant. So in particular, so furthermore, not in particular, so furthermore, for any unstable leaf, the set of points with dense forward orbit has a full Lebesgue measure. Okay. So if I concentrate on any single, any specific unstable leaf, into the future, most points on it will be dense. Okay. In fact, you have things not just density, you have that they spend equal time in equal regions of space. All right. Any questions about any of this? All right. So I eventually want to prove a theorem that I stated in the first lecture. So I realized that it might make sense to prove. So I'll start the proof now, and I'll break it down into 3 steps. And I'll prove step 1 today, and step 2 and the necessary tools next time, or depending on how it goes, maybe I'll start today as well. Okay? So now we're going to use some of this information to start the proof of the theorem.
So can we say from one of the corollaries that there could be stable leaves for which there is no point which is dense?
I'm sorry, say it again?
There could be stable leaves where there is no point on the stable leaf is under the geodesic flow.
Yes.
But on the unstable leaf, there is no such unstable leaf.
But if I'm looking into the future. Yeah, so there's a symmetric statement for the, but you have to reverse all the words. So the time and the stable with unstable. Yeah. So there could be stable leaves. So for example, suppose you have a periodic orbit, then all the points which are stably related to that periodic orbit, they'll not be dense. They'll be asymptotic to that periodic orbit. But if I take the unstable leaf, they will expand, and then most points will visit everything. Right. Any other questions? No. Okay. So let me recall what we're trying to do. So if we have that if n is at least 3, n-dimensional is a real-analytic, negatively curved Riemannian manifold, with infinitely many, let's say, closed, immersed, totally geodesic hypersurfaces, then M has constant sectional curvature, meaning that it's isometric to a quotient of hyperbolic space. OK, so this is what we're after. And so let me introduce a little bit of notation for the proof. So we already have UM. This is the unit tangent bundle. So I'm going to introduce HM to be the oriented hyperplane bundle. So if a point in UM above is just a unit tangent vector, a point in HM is a choice of a hyperplane in that tangent space with an orientation. So you'll not be surprised to note that these two spaces are actually isomorphic. Right? To give an oriented hyperplane is the same as to give a normal vector. But I want to think of them as distinct spaces. And I'm going to denote by FM the set of pairs VH inside, so V inside a tangent space, a unit vector, and H contains V, oriented hyperplane. And so this FM is nothing but pairs of two orthogonal unit vectors. So it's a partial frame at each tangent space, because if you have the first vector is V, and the second one is the orthogonal complement to H, the one that gives you the orientation. So these three spaces sit in a diagram. So we have FM sitting above UM and also above HM. And we have M at the bottom. So in a moment, when we go into the proofs, we're going to do some dimensional calculations. So it's good to, I'm going to make the copy of this diagram where I just put the dimensions of each space, just so we can keep track of things. So this is n-dimensional. OK, so let me see if people are awake. So what is the dimension of this space?
2n minus 3.
Sorry?
2n minus
2n minus 1 because the fiber is an n minus 1 dimensional sphere. So each of these spaces in the middle, they have dimension 2n minus 1. And the fiber here is a sphere of dimension n minus 1. And maybe if I ask you what is the dimension of the fiber, say in one direction. So just the fiber will be n minus 2 dimensional, right? Because there's if I choose one vector in the unit sphere, then the orthogonal complement is another n minus 2 sphere, right? So I have to add n minus 2 to this, so I get 3n minus 3. So the dimensions, the fiber dimensions, if I put them like this, so I get. Okay. So I'm going to now introduce a few more sets. So Z is going to be the set of hyperplanes H such that exp of H is totally geodesic. So here by exp I mean the exponential map. So if I have any hyperplane, I can take its exponential map, and it gives me a hypersurface. And I'm just asking for this hypersurface to be totally geodesic. I'm not asking it to close up or anything like that. So it's a purely a statement about whether, when I exponentiate it, it keeps staying totally geodesic. Okay. I'm going to denote by, so let me give these maps names, pi h, pi u. So I, kind of the incidence set, is going to be pi h inverse of z, and a is going to be pi u of I. So what is, if you follow through the definitions, this is the set of unit vectors, unit tangent vectors, through which there exists some totally geodesic hyperplane, or hypersurface if you want. So at this stage, I no longer need things to be closed. When I say totally geodesic, I just mean, when you exponentiate it, it gives you something totally geodesic. Right, so these spaces, they also sit in the same kind of diagram. I have I sitting above Z and sitting above A. So as I mentioned, the proof naturally breaks into 3 steps. So in the first step, which hopefully we'll finish today, is we'll prove that A is equal to which means that for every unit tangent vector, there exists some totally geodesic hyperplane. Step 2 is going to be that Z is equal to HM, meaning that every hyperplane exponentiates to a totally geodesic hypersurface. And step 3, we profit, so we just invoke Cartan. There's a theorem from many years ago, which is due to Cartan, that if n is at least 3, and every hyperplane in a Riemannian manifold exponentiates to something totally geodesic, then M has a constant sectional curvature, so this means that locally M is Rn, Sn, or Hn. And of course, we can only be in the last case. So step 3, I'll just say 2 words now, and then I'll never come back to it. So today we'll do step 1, and then we'll move on to step 2. So Cartan's theorem is purely local. In other words, it's just a statement about a small open set in Rn. And basically, the proof goes in 2 stages. One is you use all sorts of games with the Riemann curvature tensor to show that at a single point, if you have this totally geodesic property, then at a single point, the sectional curvature has to be constant in every 2 plane. So this is just a lot of linear algebra. And then the next step is now you have a function on your small open set, which is the sectional curvature at that point. And then you need to also make sure that that function is constant and not just some arbitrary thing. And again, it's a purely local argument to draw that conclusion as well. So this step 3 is purely local and very old. OK? I should maybe add as a side comment that these kinds of theorems have been generalized in many directions. So many other symmetric spaces can be characterized by these kinds of conditions, again, in purely local terms, and also to higher codimension. So you don't need to assume necessarily hypersurfaces.
Can you say one more word about the second part of step 3, why the function is constant?
One word, I mean, then Spivak. So there's a proof in Spivak's, and it's not long. I'm forgetting right now, but it's nothing too sophisticated because it doesn't use any maximum principle or anything like this. It's just you differentiate maybe, and it comes out. I don't know. OK. Any other questions about the proof outline?
So just to clear, so it's just Aristotle geodesic. You don't need to know it's also hyperbolic.
For step 3? Sure. Yeah, so Cartan's theorem is just about totally geodesics. Yeah. So in particular, the conclusion, it doesn't tell you what the sign of the curvature is. It could be positive, negative, or 0. OK. Any other questions? All right. So let's move on to step 1. So in step 1, we're going to use the crucial assumption that the Riemannian metric is real-analytic. So this is a very strong assumption, which we'd like to be able to drop, but we cannot, at least for the moment. So let me recall a few things. So I'm going to say that a subset S inside, say, Rn, or any other kind of analytic manifold so we're going to say that it is analytic if it is the 0 locus of finitely many analytic functions so in fact, finitely many is not necessary. So if you're 0 locus of infinitely many, then you can restrict to a finite subset of it. We're going to say that it is semi-analytic if, so semi-analytic is a bit more involved, so it is of the following form, Fij, and then sigma ij 0. So I intersect over all j, and then here you take union over all I, and sigma ij is a symbol, so it could be either greater than or equal to. So now I allow myself to take regions where some particular analytic function is positive, or if I take the negative function, then negative. I also allow myself to set some analytic functions to 0, and allow myself to intersect and take unions of such things, but only finitely many. So if I were to replace analytic with algebraic, so real algebraic polynomials, then there's a very nice theorem of Tarski and Seidenberg that tells you that if you project a semi-analytic set, you obtain, or semi-algebraic set, you obtain another semi-algebraic set. Unfortunately, this is not true for analytic functions. So we're going to say that a set is subanalytic if it is the image under a proper map of a semi-analytic set. Actually, I should probably not use a hyphen here. So if you wrote it, just erase it. So of a semi-analytic set. So there's a nice exercise that I encourage you to do. So if I take the following function phi from R2 to R3, and it's x1, x2 goes to x1, x1, x2, x1, x2, e to the x2, then there does not exist a formal series G of y1, y2, y3 such that G composed with phi is identically 0. So what is this exercise telling us? It's telling us that, so I take the R2, or I could restrict it to a unit disk in R2. So I map it under this map that I wrote there, phi, to R3. I get some surface, maybe a little bit singular. And the claim is that there does not exist even a formal series which vanishes exactly on that surface. So if you took a polynomial map here, then in fact such a polynomial function would exist. So this exercise shows that subanalytic sets are, so this is the image of this map. If you take a small neighborhood of 0, the image of this map is a subanalytic set, which is neither analytic nor semi-analytic. Okay? So this is some kind of class of sets. But the nice thing is that once you pass to subanalytic sets, you're done. So it's a fact.
And just, when you say proper map, you mean proper?
So I mean that there's a proper, maybe either, so you maybe have a compact manifold with boundary if you want, and there's a proper map from that manifold to analytic. Yeah.
Analytic.
Yeah, the map is analytic, and by proper, yes, proper, certainly, proper and analytic. Yeah. This was kind of assumed. I apologize. Okay, so the fact about subanalytic sets is that subanalytic sets have a good notion of dimension. and stratifications with good properties in particular the smooth sublocus is itself subanalytic. There's a slight lie here, but don't worry. Okay, so they have the subanalytic sets form a nice geometric category in which you can kind of play with things. And there's a proposition which is not very hard to prove, which is that, so if I go back to my diagram here, yeah, so smooth, I mean that, so I have a notion of dimension, and so if I have this subanalytic set, there's I can talk about having a tangent space there and being isomorphic to some manifold. Okay. All right, so back to M, UM, HM, AZ, and Y. So the first statement is that Z and I are analytic sets, and A is subanalytic. So basically the only thing I need to prove is that Z is analytic because I is the preimage of Z under a proper map, but the preimage of an analytic set, it's also cut out by the same analytic functions if you pull them back, and A is tautologically the push forward, what you get by projecting down I. Okay, so the only thing is I have to maybe make an argument about Z. So suffices to show Z is analytic. But whether a hyperplane exponentiates to totally geodesic hypersurface can be described by vanishing of the second fundamental form. So some concept from Riemannian geometry, and which gives, let me just say, some analytic conditions on the Taylor, on the, so there's a little calculation which if you can look in the paper, but essentially I have my hyperplane and I'll give myself not just the metric, the value of the Riemannian metric on that tangent space, but all the higher order jets of that Riemannian metric. And from that, I can compute this second fundamental form, and not just the second fundamental form, but also its higher order jets on this hypersurface. And the vanishing of the second fundamental form, the identical vanishing, is what this totally geodesic condition is equivalent to. And if you have this real-analytic object, the second fundamental form, and if its whole Taylor series vanishes, then it vanishes, and vice versa.
Yeah, but doesn't that require an X map to be written analytically?
Yeah, so the exponential map is going to be a real analytic map, at least if you restrict it to, let's say, a ball of radius 1. if the metric is real analytic, then the exponential map will be also real analytic. Yeah. So if you have an ODE, a real analytic ODE, the solutions are also real analytic. Okay. All right. Any questions? All right. So let me move on to the dimension count. So okay. So proving A is equal to UM. So we have these totally geodesic hypersurfaces inside M, totally geodesic. They lift to SI tilde. If I map, so if I have it's an immersed hypersurface, but at each point I can take this tangent hyperplane and I lift it to the hyperplane bundle. So this has dimension n minus 1. So but of course this factors through z. So if I have infinitely many SI tildes, implies that the dimension of z is at least n, because each of them has dimension n minus 1. So infinitely many of them can only be contained, if they're distinct, it can only be contained in a set of dimension at least n. So this implies dimension of I is at least dimension of z plus, so the fibers, remember, have dimension n minus 2. So this is, sorry. So this is greater than or equal to 2n minus 2. So now if I concentrate in this part of the diagram, so A, this is inside UM. So this has dimension n minus 1, 2n minus 1. So you see that I projects onto a set A, and A sits inside something of dimension 2n minus 1, and I is 2n minus 2 dimensional, so it's pretty close. Right? So you would expect things to be quite nice. So there's two cases. The first case is that dimension of A is also at least 2n minus 2. So I projects essentially 1 to 1, or at least without positive dimensional fibers. And the second case is that I to A has a fiber of positive dimension. So I'll explain case 1. Case 2 is very similar. So let's think for a second about what case 2 says. It says there's a tangent vector for which there's a one-parameter family of hyperplanes that are totally geodesic. So those totally geodesic hyperplanes, they sweep out some fairly large set in the manifold M. But using games that I'll show you in a moment in case 1, you can prove by similar arguments case 2. So I'll just treat case 1. So A is closed and GT invariant. It suffices to find one point with a dense orbit. So I'm going to take A naught inside A, the smooth locus, and A inside A naught. So because A is invariant by the flow, in the tangent space I have the flow direction. So I have the tangent at A to A naught. If I quotient the center direction, this is contained in the unstable plus the stable direction. So these are n-1 and n-1 dimensional. And this is 2n-3 dimensional. So if the dimension was strictly greater than 2n-3, then I would get, of course, this would be surjective. And this means that A contains an open set in UM, and being, certainly points with dense orbit are, dense. I mean, they're full measure in any open set. But even so, we can say either way with certainty that this subspace has to be transverse to either WU, so that is W of A, W of A, so do the red colors. So in 2 dimensions, I mean, you're either, so let's say your tangent, well, you could be tangent to the vertical direction, but you're certainly transverse to, this is A, this is little a. So you can certainly be transverse to the, let's say, to the red foliation, to the unstable. So let's say to WU of A. So this means that if I project it, so in other words, if I follow these lines, like if I project it to one of the stable manifolds, I'm going to get locally a surjection onto some open set. So projecting locally at A along W, the center unstable, to the stable leaf will contain an open set. But remember, this open set, it will be, so points in this open set with dense backward orbit will be, sorry, yeah, so points with dense backward orbit will be dense. So yeah, so points with dense backward orbit will be dense here. And this set is saturated. So if I have a point here with dense backward orbit, any other point on the same unstable is also will have a dense backward orbit, because in the past unstables contract. So I'll have a point on my set A with dense backward orbit. And this shows that A, because it's closed, it has to be everything. Okay, so this is how you prove case 1. And case 2 is kind of similar, but I wouldn't say more confusing. I think if you just read it in the paper, I hope we wrote it not too confusingly. So, but it's the same kind of argument with stables and unstables. All right, so I'll stop here, and I'll do step 2 and some other things next time.
Questions?
Okay, it must be.
Like for me, like this, I think to me like it tells us that sub-analytic sets may not be analytic. Like how can you also show like this might not be semi-analytic?
Sorry, say it again.
Like this exercise.
So what about this exercise?
Like this, I think that you want to tell us like self-analytic sets might not be analytic or semi-analytic.
Yes.
And from this argument, it's clear to me that it's not analytic, but how do you show it's also not semi-analytic?
Fair enough. I think you can work a little bit. I mean, I think I mean I don't think it's too bad to show. I mean, I think you can talk. You see, you can talk about dimension of both of these sets, and there will have to be some component. I mean, when you look at these semi-analytic sets, I mean, you. The extra freedom to put bigger than or equal to 0, or strictly bigger than 0, or strictly less than 0, it does not kind of affect your dimensions. There's still, if it's semi-analytic, there will still be some analytic function which has to vanish. So there's going to be a function here that has to vanish on the set. Mm-hmm.
All right, more questions?
Well, if not, let's thank Simion again.